All right, so we are starting on page 332, section 5.3. The whole section is about inverse functions. So the first thing it does is it defines an inverse function. A function g is the inverse function of the function f. If f of g of x equals x for each x in the domain of g, and g of f of x equals x for each x in the domain of f, the function g is denoted by f to the negative 1, which is read f inverse, okay? So if you'll remember from pre-cal when we did composite functions, inverse functions when you took the composite, which is what this is, would give you an x as the answer no matter which way you took the composite, and that's what it's saying. And then the notation we've used before as well, the inverse function is notated with that negative 1 at the top there. Show that the functions are inverses. So when you're showing it, again, this is review, you just do the composite and it doesn't matter which way you do it. So for this one, you could say f of g of x, or what you've seen before looks like this, f of g of x, which means you take the g and you plug it into the f. And so you would say f of g of x equals 2, and instead of x cubed, we're going to write the cubed root of x plus 1 over 2 cubed minus 1. And then, of course, when you cube a cubed root, the root just goes away. So we have 2 times x plus 1 over 2 minus 1. And then the 2's will cancel. So you have x plus 1 minus 1, which of course the minus 1 and plus 1 will cancel, and you're left with just x, which is exactly what you're looking for. So yes, they are inverses.
So your answer should always be x.
Your answer should always be, x if they are inverses. If it's not x, then they're not inverses. This first one's at the bottom, page 333. Theorem 5.6, reflexive property of the inverse function. The graph of f contains the point AB, if and only if the graph of the inverse of f contains the point BA. So this is also something that is a review from pre-calc world. If you'll recall when we just did number sets, when you had the inverse, you just flip-flop the x and y's. And so what the graph does is it actually reflects across the line y equals x. So this dotted line here is y equals x, and you'll see that the original function just flip-flopped across that line y equals x, which is something we also talked about with symmetry. When a graph is symmetric, it flips across this particular line here. It can be symmetric to the origin, and when it's symmetric to the origin, that's the line we use. And so you just take any function, and if you flip it across, you will see that that is the inverse of the function. And so the next theorem, which follows directly from that, as to whether or not the inverse function even exists, is based on that principle. A function has an inverse if and only if it is 1-to-1. So original functions, like if it's a function at all, it will be 1 x to y, meaning if you plug in an x, you'll only get 1 y. But you can plug in 2 different x's and get the same y, and it would still be a function. And so this is 1-to-1 both ways. So the only way it's going to have an inverse if it's 1-to-1 both ways. And so I use the example like when you're ringing up a barcode. And so you go to the grocery store and you have like bread and cookies. It's fine for a function if the bread barcode is $3 and the cookie is $3, right? What's not fine for a function is if you have 2 packs of the same bread and one barcode gives you $3 and one barcode gives you $4. That's not a function. The input gave you 2 outputs, right? For an inverse, it has to be both directions, meaning the bread can be $3, the cookies cannot be $3, or when you reverse it, $3 gives you 2 different outputs. And so for a function to have an inverse, it has to be 1-to-1, both from x to y and y to x. That's what that first thing is saying. If f is strictly monotonic on its entire domain, then it is 1-to-1, and therefore it has an inverse function. So monotonic is its 1-to-1 entire domain. And so it will have an inverse function at that point. And there's actually, I don't know why they don't actually. All right, so let's look at example 2. It says, which of these functions has an inverse? And so if you look at the first one, the f is increasing over its entire domain. So meaning, like they said in monotonic, when if it were to go up and down, then it's going to cause a problem when you flip it. But if it is going the same direction, the entire domain, you can see if I were to do a vertical line here with a vertical line test, obviously anywhere I put that, it is going to be a function. But at the same thing, if I were to do a horizontal line test, anywhere I put a horizontal line, I would only cross it once. This guy will have an inverse for sure, just by looking at that function. Let's look at the second one. This is not continuous. I mean, it's continuous, but it's not monotonic. So meaning it goes up, it goes down, it goes back up. This is not a problem for vertical line test right here. Vertical line test is going to pass. This is a function. However, horizontal line test will fail. Horizontal line test, as they show you right there, and anywhere you put it where it changes direction, this will not have an inverse. It is a function. It will not, an inverse will not exist for this particular function. So finding an inverse, guidelines for finding an inverse, top of page 335. It says use theorem 5.7 to determine if it has an inverse. Solve for x as a function of y. Interchange x and y. And the resulting equation is y equals the inverse of f of x. Define the domain to be the range of f and verify that those two work. When they say define the domain, when you have inverses, the domain and range flip-flop. Just like I said, x and y is flip-flop, x being domain, y being range. And so on your function, if your domain is here and your range is here, your inverse, those will flip-flop. So your range will now be your domain, and your domain will now be your range. So the simplest way to do this is just like we did back in pre-cal. You change f of x to be a y. So I'm going to actually write this f of x as a y. And then I'm going to switch my x and y. So instead of y equals the square root of 2x minus 3, I'm going to have, and this should look very familiar, x equals the square root of 2y minus 3. I am going to then solve for y. And so I am going to square both sides. And I will get x squared equals 2y minus 3. And then we're just solving at this point. So we're going to add 3 to both sides. X squared plus 3 equals 2y. Divided by 2. Divide everything by 2. We get x squared plus 3 over 2 equals y. And we're going to change that y back to an f to the negative 1 to indicate that it's an inverse. So f inverse of x equals x squared plus 3 over 2. All right, so this says show that the sine function, f of x equals sine of x, is not one-to-one on the entire real line. Then show that negative pi over 2 to pi over 2 is the largest interval centered at the origin for which f is strictly monotonic. Okay, monotonic meaning it does not change direction, right? And so if you look at the graph of this, so if you look at this graph, it's simple to visually see that this is not going to have an inverse because obviously it's going to fail my horizontal line test easily. The other thing to point out is that sine is a cyclic function. I mean, it's based off the unit circle. And so it is, the whole point of it is repeated values. And so you can pick you can easily pick 2 points and say, I'm going to tell you it's not one-to-one because pi gives me the same answer as negative pi. There we go. It's not one-to-one, right? It would have to mean that pi and negative pi give me different answers, and they don't. The largest interval is going to be, and of course it cycles, so it's going to happen multiple times, but this is the largest interval you will have where it does not repeat itself. And it will happen again going to the left and going to the right. But this is the largest interval where it is monotonic, where it is one-to-one. That's the largest interval on this function. Obviously, you can have 2 sine of x or something, and it would change what's happening with sine. But for sine of x, that's the largest interval, what doesn't repeat, and then as soon as you start from there, it's going to repeat again. And so this is not going to be a one-to-one, and it's not going to be monotonic where it doesn't go back down. Because even in this group right here, this is not one-to-one, because you're going to have 2 points even in this part that gives you. So it's only the part that's either here or from here going forward back to, across here. And so you'll have sections that are one-to-one, but over the cycle of the graph itself, it's not one-to-one. So sine does not have an inverse. Reciprocal functions and inverse functions are 2 different things. Reciprocal function of sine would be cosecant. We know that exists. But inverse function is different. Inverse function is not the same as reciprocal function. So let's first look at the theorems for continuity and then derivatives. Let f be a function whose domain is the interval I. If f has an inverse function, then the following statements are true. F is continuous on the domain, then the inverse is continuous. If f is increasing on the domain, then the inverse is increasing. If f is decreasing, then the inverse is decreasing. If f is differentiable at c, and the derivative of f at c does not equal 0, then the inverse is differentiable at c as well. So here's the theorem. Let f be a function that is differentiable on the interval I. If f has an inverse function g, then g is differentiable at any x for which f prime of g of x does not equal 0. Moreover, the derivative of the inverse is 1 over the derivative of the composite of those 2. All right? So let's look at it in action. So the first thing is they give us this function, f of x equals 1/4 x cubed plus x minus 1. All right, it says what is the value of the inverse of f of x when x is 3? And what is the value of the inverse of the derivative of x when x is 3? All right? So the first thing we look at is what happens for f of x. So when f of x equals 3, what is x, right? And so the first way, obviously they give us the graph. There's another way to do it mathematically if you do not have a graph. So we'll look at it both ways. All right, so let's look at the graph first. Or when y is 3, x is 2. If I did not know that, though, I could solve for it. I could plug a 3 in, right? I could subtract the 3 over, and then I could solve for it when it equals 0. And so if you don't have the graph, you have been given a y value and you're solving for x. Plug in the y value, solve for x, right? And you can do that just by factoring. But we know just based on what they've given us that my x value here is 2 when my y is 3, because we can see this point, 2, 3. All right? And so that means, so they're asking, what is the value of the derivative then? So for this first part, I would say f of 2 equals 3, x and y. They are asking for what happens when with f prime then of 3. Well, remember my x and y's switch places with my inverses, right? So if my original x is 2 and y is 3, then for my inverse, when x is 3, y should be 2. They switch places. So that answers the very first question there. So this particular function has a derivative and it has an inverse, because we can see that from the graph and we can see that from the one-to-one relationship. Now it wants us to say, I want you to find the derivative of the inverse at 3. So they want me to now do the derivative of the inverse. So that's my inverse and that's the derivative notation when x is 3. And so then this is when I'm going to go back to my formula that they gave me. All right, so the formula they gave us for The g being the inverse of f, right? That's what they gave us. So in the explanation over there, g of x is the inverse of f. So they're talking about, you could write that both ways. This is what we're looking for. So the inverse of a function at a point, if I'm taking the derivative of the inverse is going to be 1 over the derivative of the composite, or what happens when you plug it in. All right, so if I were to do this one like that, I would say, well, the derivative of the inverse of f should be 1 over the derivative of the original function with the inverse of the function of the number I'm looking for. Okay? So 1 over the derivative of the original function of the inverse of the number that I'm looking for. All right, so first thing then, how do we find this inside piece right here? Well, think about it. This is just the y value from my original function, and I'm asking for the x value from my original function. So that's what I did up here, right? If they're asking for the inverse at 3, then they're asking for what x gives me the y value of 3 of the original function. So that part, I'm just filling that in with a 2. So that's 1 over the derivative at 2. All right? So then how do I find the derivative at 2? Well, I take the derivative and plug in a 2. So I'm going to go back to my original function, and I'm going to take that derivative. And so I'm going to say, well, the derivative of 1/4 x cubed, that is 3/4 x squared, plus the derivative of x is 1. And then, of course, my -1 goes away because it's a constant. So just straight derivative. And I'm going to take that 2 and plug it in. So this is going to be 1 over 3/4 2 squared plus 1. 2 squared is 4. 3/4 times 4 is 3. Plus 1 is 4. So 1/4 would be my value there. So the derivative of the inverse at 3 is 1/4. So that means, like, what does derivative tell us? It tells us slope of the tangent line. So the slope of the tangent line of the inverse function at 3 is 1/4. The slope of the tangent line at 3. And so this is where you find that right here. So let's look at what happens here. Just the inverse at 2, the slope is 4, right? So if I'm finding the derivative at 2, I found the slope of the tangent line at 2. That was 4. That was my denominator. If I want to find the slope of the inverse at 3, that's 1/4. So you'll notice two things that happen here. If you are looking at those points that reflect, their slopes are reciprocals of each other. And you have to make sure that you go back to your original knowledge of derivatives. What's the first thing derivative told us? Slope of the tangent line. And so if I find the derivative of this function at 2, I'm finding the slope of the tangent line. If I find the derivative of the inverse function at 3, I'm finding the slope of the tangent line. 3, 2 is a point on the inverse. 2, 3 is the point on the original function, because that's what happens with functions and inverses. And so if I take those, the slopes will be reciprocal, which is actually what the next one tells us. It says that graphs of inverses have reciprocal slopes. That's exactly what it tells us. It says let f of x equal x squared. For greater than 0, inverse of x is going to be square root of x. Show that the slopes of the graph are reciprocals at each of the following points. And you can do it two ways. You can use your straight up slope formula, or you can do it with what we just did, derivatives. So if you did derivatives, you could 2x and then 1/2, 1 over 2x to the negative 1/2. We'll do it both ways. Or you could use your slope formula and show that they're going to be reciprocals of each other. So if 2, 4 is on my graph, 4, 2 is on my inverse. If 3, 9 is on my graph, 9, 3 is on my inverse. So that means this is 2 points on my graph. This is 2 points on my inverse. So if we do it the first way, and we just say, let's just do our slope formula. My slope formula, remember, is y2 minus y1 over x2 minus x1. So let's do the original function. So my original function would be the 2, 4 and the 3, 9. All right, 2, 4 and 3, 9. And so we will just do that 9 minus 4 over 3 minus 2. My slope here is 5. So I'm just doing the slope of the actual graph itself between these 2 points, and we're going to do it at the exact points in just a second, but just to show you this one, if I do this one right here, then I'll have 3 minus 2 over 9 minus 4, and I'm going to get 1/5. So even between those 2 points, you can see that my slopes are going to be reciprocals. If they wanted at a specific point, like now we're talking slope of the tangent line, not just slope of the graph, all right? That's just slope between those points. Let's look at the slope of the tangent line. All right, so let's take the first one. Let's take this guy right here, my original function. And let's say my derivative then is going to be 2x. So if I want my slope then at, let's say, the point 2, right? Then I should get 4, right? Let's take my second one, this function right here. And let's do this derivative. The derivative of this guy, right, is going to be 1 over 2 square root of x. That's my derivative because it's x to the 1/2, multiply by the 1/2, take it, subtract 1. So that's how I get 1 over 2. And I now need to check the point 4, 2, because that's what goes along with this one. So if I check that and say, well, I'm going to do that at 4, I get 1 over 2 square root of 4, which is 1 over 4. They are reciprocals at that point. The slope of the tangent lines are reciprocals at that point.